Welcome back. We're talking about the proximal gradient algorithm, and we're going to derive rates of convergence for composite functions where our function is smooth or smooth and strongly convex. So to remind you of the setting, we're trying to minimize a function f of x, which is equal to the sum of two functions, g of x plus h of x, and we're assuming that g of x is beta smooth and possibly alpha strongly convex, and h of x is convex, and no further assumptions except that it has a proximal operator which is easy to evaluate. So we're being intentionally vague about that. So this is convex and easy to evaluate Prox operator. Our algorithm is proximal gradient descent. X t plus 1 is equal to Prox eta h of xt minus eta gradient of g of xt. We're taking eta typically to be 1 over beta. Beta is a smoothness parameter of g. And we've defined the gradient mapping to be such that I can write xt plus 1 is equal to xt minus eta times g eta of xt. So starting from the desire to have this, the gradient mapping has to be equal to 1 over eta times x minus the prox eta times h of eta h of x minus eta times the gradient of g of x. And the key lemma that we're going to prove and then use for the rates of convergence tells me that as long as we take step size less than 1 over beta, then f of x minus eta g of x, in other words, this would be my next iterate, f of xt plus 1, is less than or equal to f of z, this is true for any z, plus g eta of x times x minus z, minus eta over 2 times g eta of x squared, minus alpha over 2 x minus z squared. So note that this last term here, because of the way the inequality goes, if alpha is greater than 0, that's great. That just improves this. It improves this bound. But if alpha is equal to 0, then things are still okay. So we need to prove this key lemma. Okay, so let's again write out the first term, f of x minus eta g eta of x. This is what I need to upper bound. This is what the lemma does. Now, just by definition, this is equal to g plus h. So it's g of x minus eta g eta of x plus h of x minus eta g eta of x. And I'm going to bound these two separately. So let me call this term A and this term B. So term A is upper bounded. This is the easy one because g is not only convex, but it's also smooth. So this is upper bounded by g of x minus eta times the gradient of g of x, g eta of x, plus eta over 2 times g eta of x squared. Where did this come from? Give you a second to think about it. So this is directly from the smoothness. So it's just applying the quadratic upper bound from smoothness of g. In turn, this is now, I'm going to upper bound the term g of x. This is less than or equal to g of z minus the gradient of g of z times z minus x minus alpha over 2 times z minus x squared. And now I have just the other two terms that I had above. So minus eta times gradient of g of x, gradient mapping of x, plus eta over 2 times g eta of x squared. So it's this, so all I did here, so g of x was upper bounded by this term. The other two terms are exactly the same. Where does this come from? This is strong convexity. Strong convexity. Okay, so this was the easy part. Now let's look at B. We're going to need a little bit more work here because we have less structure on H. So I need to upper bound h of x minus eta g eta of x. So how do we typically upper bound something if we just have a convex function? I need an element of its subdifferential. So to upper bound, really we need an element of subdifferential of h of x minus eta g eta of x. And so specifically what I'm saying is to upper bound h of x minus eta g eta of x, I need some element of its subdifferential. So what is in their subdifferential? So again, this is, you can see why we've done similar exercises throughout, practicing with the proximal operator. So remember that we've used this several times now. If u is equal to the prox of eta h of x, then this is equivalent to writing that x minus u is in eta times the subdifferential of h of u. And we've used this a few times. Okay, so let's see what x minus eta g eta of x is. So x minus eta g eta of x, I'm just going to plug in the definitions here. This is equal to x minus eta, and let's write out again what g eta is. It's on the previous page. It's equal to 1 over eta times x minus the Prox operator, eta h, of x minus eta gradient of g of x. Okay. The etas cancel, the x's cancel, and what we find is that this is equal to the Prox. So again, the etas cancel. I have x minus x, that goes away, and then minus Prox is going to be my plus Prox. So this will be plus Prox of eta h of x minus eta gradient g of x. So we're back to this situation where we can use this relationship. So what this tells me is that, let me just write it a little bit more cleanly. So putting these two underlined things together, we find that x minus eta g eta of x is equal to Prox eta h x minus. And this is exactly telling me, using this relationship above, that g eta of x minus gradient of g of x is an element of the subdifferential of h x minus eta g eta of x. So I started out needing an element of the subdifferential of h evaluated at x minus eta g eta, and I just found one. So I have one. So now I can use convex inequality. So let's copy down what we just learned. We just saw that g eta of x minus gradient g of x is an element of the subdifferential of h evaluated at x minus eta g eta of x. And therefore, I'm going to use this element of the subdifferential to bound. So h of x minus eta g eta of x is less than or equal to h of z minus, I'm going to put now the element I found in the subdifferential, g eta of x minus the gradient of g of x. And then what goes here? Well, it has to be the difference of the 2 points where I'm evaluating. I'm evaluating h at z, and I'm evaluating it at x minus eta g eta of x. And the relationship there, we always get that by an element of the subdifferential. So what goes here again is just z minus the other point, x minus eta g eta of x. Again, there's lots of notation here, and so it's important to at least get the basic picture of where the inequalities are coming from and what the conceptual flow is. Okay, so now we just have a bunch of terms. We need to combine them. So I need to combine, this was my bound B. I need to combine A plus B. And what we're going to find, let me just flip back just so you can get a glimpse of what A is. And so we're trying to upper bound f of x minus eta g eta of x. This is equal to A plus B, and now we've upper bounded A, we've upper bounded B, and we need to add these together. So what we get is that f of x minus eta g eta of x, if you write out all of these terms and you multiply them all out, so write out all of these terms, you'll find that this indeed gets us what we want. This is then finally equal to f of z plus g eta of x times x minus z minus eta over 2 times g eta of x squared minus alpha over 2 x minus z squared. Just to get a little bit of an idea of where these come from, A plus B, let's look at where this f of z came from because we hadn't seen an f anywhere. If you look at B here, the first term is h of z. Let's flip back and look at what the first term of term A is. First term of A is g of z. So when I add them, I have g of z plus h of z, which indeed is f of z. So it's a good exercise just to put everything together and track to make sure that that indeed things cancel and comes out in this way. Okay, so now let's look at the consequence of this. I want to look at the rate of convergence for f of x equal to g of x plus h of x when alpha is equal to 0. In other words, when I have a smooth but not strongly convex function. The lemma with z equal to x star and x equal xt gives me f of xt plus 1. Remember, this was just f of xt minus eta g eta of xt, the whole purpose for defining the gradient mapping, is less than or equal to g is less than or equal to f of x star. Remember, the first term was f of z. Z is equal to x star, so I've got f of x star plus g eta of xt times xt minus x star minus eta over 2 times g eta of xt. You should compare this. And so note that basically I can bring f of x to the other side and compare this to our proof for smooth functions. So for smooth functions from several lectures prior, we had f of xt plus 1 minus f of x star is less than or equal to gradient of f of xt minus x star minus eta over 2 times gradient of f of xt squared. You see again, this looks almost identical with the gradient mapping playing the role of the gradient function. Okay, so continuing, what we find is that f of xt plus 1 minus f of x star, I'm just rewriting this, is less than or equal to g eta of xt minus x star minus eta over 2 g eta of xt. This is, in turn, less than or equal to 1 over 2 eta, same exact game with quadratic that we've seen many, many times before at this point, xt minus x star squared minus xt minus x star minus eta g eta of xt. But what is xt minus eta g eta of xt? It's just xt plus 1. This is equal to 1 over 2 eta times xt minus x star squared minus xt plus 1 minus x star. And we're back with our friend, the telescoping sum. Exactly what we've seen before. So we find that f of xt minus f of x star, if we sum everything from 1 to t and divide by t, is less than or equal to 1 over t sum of f of xt minus f of x star, which is less than or equal to 1 over 2 eta t times the first term in the sum minus the last term in the sum. x1 minus x star squared minus the last term, xt minus x star squared. We drop the last term and we get our result. 1 over 2 eta t times x1 minus x star squared. This is order 1 over t convergence. Again, it's worth taking just a moment to appreciate what's happened. We had a function that's not smooth because g and plus h is not smooth, yet we got faster convergence than the lower bounds say. So how could this possibly be? It comes because we're not using the oracle model anymore. We're using this proximal operator. We're not just operating with subgradients of f. If we were, we would have no choice but to be bound by the lower bound results. We can very quickly modify this to get the proof of the rate of convergence for smooth and strongly convex. So similarly to what we had before, we have f of xt plus 1 minus f of x star is less than or equal to g eta of xt minus x star minus eta over 2, this is the terms that we saw before, g eta of xt. And the only additional term is this minus alpha over 2 times xt minus x star. Again, playing the same tricks as before, this is equal to 1 over 2 eta times xt minus x star squared minus eta alpha times xt minus x star squared minus xt plus 1 minus x star squared. Where did this eta come from? I had alpha over 2, but I brought it inside the parentheses. I'm dividing by 1 over 2 alpha. So 1 over 2 eta. 1 over 2 eta times eta alpha is my alpha over 2. This is equal to 1 over 2 eta times 1 minus eta alpha xt minus x star squared minus xt plus 1 minus x star squared. And note that the left-hand side is actually greater than or equal to 0 because f of xt plus 1 minus the optimal solution is always going to be greater than or equal to 0. So in that case, I can bring xt plus 1 over to the left, multiplying by 1 over 2 eta to get rid of that, and I get xt plus 1 minus x star squared is less than or equal to 1 minus eta alpha times xt minus x star squared. And note what this is. If I choose eta equal to 1 over beta, which is typically what I'm going to choose, we know that that's the optimal step size to choose as far as minimizing that quadratic upper bound, then this is equal to 1 minus alpha over beta times xt minus x star squared, or 1 minus alpha over beta to the t times x1 minus x star squared. So I've gotten back my linear convergence. And note that I've got my kappa here just as before. So I basically get the exact same rates that we had before. That brings us to the close of our rates of convergence for proximal gradient. We're going to pick it up next time.